Thanks for the invitation and for the introduction. That was a mouthful. So I do computational material science, and the science fiction fantasy of computational material science is that someday I'll be able to ask my computer for a material with some desired properties, for example, room temperature superconductor, and the computer will think about it for a few minutes and send the instructions to the atomic assembly unit, and then just hand it to me with my coffee. So now for the reality of computational materials design. The advantage of designing material on the computer is that on the computer we can do whatever we want. We can arrange the atoms however we want. And so we can explore the uncharted territories of materials that haven't been made yet. And we can scan through structures and compositions faster than is possible experimentally because conveniently we don't have to actually make or measure anything. And then if we have a good algorithm for scanning that configuration space, we might be able to come up with unintuitive solutions. So you can see how computational materials design can accelerate the discovery and the deployment of new materials. So my favorite materials are molecular crystals. And if you're wondering what's so interesting about molecular crystals, well, as you may know, a molecule is held together by chemical bonds between atoms, where there is some overlap between the electron densities of different atoms. But in the molecular crystals, the molecules are pretty far apart. So there's no overlap between the electron densities of neighboring molecules. Well, what's holding them together then? It's van der Waals, also known as dispersion interactions between these molecules. And dispersion interactions arise from quantum mechanical fluctuations of the electron density that produce instantaneous dipoles and higher order multipoles. And then the electrostatic interaction between these dipoles produces a weak but long-ranged attractive force. And these are the van der Waals interactions. So actually, even though the van der Waals interactions are weak, their cumulative effect can be pretty strong, strong enough to stick a gecko to the ceiling. So geckos have on their feet millions and millions of these tiny nano hairs, and each one of these nano hairs is interacting with the surface through van der Waals interactions. And the sum of all these interactions is enough to stick the gecko to vertical surfaces. So molecular crystals are used in applications in pharmaceuticals and in nonlinear optics, and also in organic electronics. And the thing is that the weak nature of van der Waals interactions produces potential energy surfaces that are very shallow, and they have lots and lots of energy minima that are very close in energy. So, for example, if a typical inorganic compound has a potential energy surface that looks like this, and you have one form that's significantly more stable than the other possible structures, that is a monomorphic potential energy landscape. But for molecular crystal, the situation looks more like this, where you have several different structures that are very close in energy, and you might actually see more than one of them. And this is called polymorphism. So the thing with polymorphism is that different crystal forms of the same molecule might have pretty different physical and chemical properties. So if, for example, it's a molecular crystal of a drug, then if you accidentally get the wrong crystal form, that might hurt the bioavailability of your drug, for example. So therefore, we're very interested in being able to predict the existence of these polymorphic forms of molecular crystals. But the challenge is that the energy differences between polymorphs can be extremely small, less than 0.1 kilocalories per mole. And so to reach that kind of accuracy in the energetics, we have to go to fully quantum mechanical simulations. And here, the challenge is that even in a very small system, there are many, many, many interacting electrons. In fact, there are more electrons in a penny than stars in the known universe. So that's the problem we have to deal with. And in Dirac's words, the laws of quantum mechanics are completely known. However, it's impossible to solve the equations exactly, pretty much for anything with more than one electron. So therefore, we have to come up with approximate practical methods of applying quantum mechanics to complex atomic systems. And this is what electronic structure theory is all about. So it's an art of approximation. And we have different types of approximations that we can use to describe different types of materials' properties that are associated with different types of electronic processes. So for ground state properties, like the structure of a crystal or the mechanical properties, we have density functional theory, DFT, that was already mentioned here a couple of times, and that is a ground state theory. But many properties of interest are actually associated with electronic excitations. So one set of properties here are associated with charged excitations. That's when an electron is being added or removed from your system. And these properties include things like ionization potentials, electron affinities, band gaps, and so on. So if you want to describe these processes correctly, then you have to take into account the electronic response to the addition or removal of one electron. And this is what we do in a method called GW, where G is a Green's function and W is the screen-Coulomb interaction. Now, the third set of properties here are associated with neutral excitations. That's when your electron is being excited into an empty state, but it doesn't leave the system, and so it interacts with the hole that's left behind, and this is called an exciton. So in order to describe this exciton, you also need to take into account the electron-hole interaction, and for this, we have a method called BSE, the Bethe-Salpeter equation. So we can use this method to describe properties like optical absorption. So now the question is, can DFT accurately predict the structure and energetics of molecular crystals? So here's an example, the polymorphs of glycine. Glycine is the smallest amino acid, and beyond its biological importance, it's also an example for hydrogen-bonded networks, which is a very common binding motif in both naturally occurring and artificially engineered molecular crystals. So glycine has 3 polymorphs. 2 of them, the alpha and beta forms, are based on sheets of glycine molecules. In the beta form, the sheets are just stacked on top of each other. And in the alpha form, they form bilayers that are bound by weaker hydrogen bonds. The gamma form is a little bit different. It actually has helices of glycine molecules in the C direction, and then the helices are bound by weaker bonds in the AB plane. So the energy differences between the three polymorphs of glycine are extremely small. You can see that the difference between the gamma form, which is the most stable, and the alpha form is less than 0.1 kilocalories per mole. And then the beta form is the least stable. It's also not far behind. So actually, in standard DFT functionals, the situation is that they don't describe van der Waals interactions very well. Here you can see an example for the AB plane of gamma glycine, and this is a typical DFT functional, PBE, and this little cross is the experiment. That's where we're supposed to be, but you can see that the minimum is somewhere over there, pretty far away. So the simplest way of dealing with the situation is to add the leading order of the dispersion interaction, the C6 over R to the 6th term, in a pairwise manner on top of the DFT functional. And this is what we do in this TS correction. And as you can see here, that gets us closer to the experiment, but still not quite there. So actually, two effects are missing here. One is the long-range screening that every atom experiences, even from atoms that are very, very far away. And the second effect is higher order interactions between 3 atoms, 4 atoms, 5 atoms, and so on. So once we take that into account in a method called many-body dispersion, or MBD, that gets us to the right place. And with DFT plus MBD, we can also describe correctly these tiny, tiny energy differences between the 3 polymorphs. So here, the dashed lines are the experiment. You can see it's a very difficult target here. And with a pairwise correction, we're getting the order of the polymorphs wrong, and also the energy differences are too large. But with the MBD method, we can recover about 0.3 kilocalories per mole of accuracy here. So, okay, we can describe the structure energetics, and the next thing we want to know is how crystal packing affects the electronic properties of molecular crystals. And why do we care? Because we want to make organic solar cells. So in a typical organic solar cells, you have an acceptor species and a donor species, and each one of them can absorb a photon and generate an electron-hole pair. But to actually have an electrical current, you need to separate these electron-hole pairs, and so it's the energy difference between the electron affinity of the acceptor and the ionization potential of the donor that's responsible for the charge separation. So organic solar cells have several appealing advantages. For example, they're cheap, they're made of earth-abundant elements, and you can make them over large areas and over flexible substrates with odd shapes, with all kinds of solution deposition and printing techniques, which is great. And also you have this infinitely vast chemical compound space that you can play around with and tune their properties, which is also great. However, their efficiencies are typically much lower than the conventional inorganic solar cells. So that's a problem we have to deal with. So there is hope for making more efficient organic solar cells, and one possible way we might be able to do that is by harnessing this different type of quantum mechanical process called singlet fission. So in singlet fission, we have one molecule here that absorbs a photon and produces an exciton here. But then somehow the singlet exciton might split into two triplet excitons localized on different molecules, and each one of them has about half the energy of the singlet exciton. So this is a spin-allowed transition because the total spin of the two molecules together is still 0. And so then you might be able to harvest the two triplet excitons, and then you end up with two charge carriers for the price of one photon, which means that you might be able to increase the efficiency of organic solar cells by twofold. So singlet fission is a complex collective quantum mechanical process whose mechanism is still debated. However, one thing is clear, which is that energy has to be conserved. So the energy conservation criterion for singlet fission to happen is that the singlet energy has to be more or less equal to twice the triplet energy. However, there's a reason why singlet fission solar cells haven't been made yet, and the reason is that, first of all, very few materials actually obey this energy criterion for singlet fission. And second, there are some difficulties with harvesting the triplet excitons. So the problem we're trying to address is the problem of finding new materials for singlet fission. I'm going to skip this because I don't have a lot of time left. So the question is now, can we improve singlet fission just by manipulating the crystal packing of molecules in a molecular crystal? So we're going to take a very well-known organic semiconductor, rubrene. Rubrene is famous for its very high mobility, which is even higher than that of amorphous silicon. So this is a rubrene molecule. It has a tetracene backbone and then 4 phenyl rings on the side. And it usually crystallizes in this orthorhombic structure that you can see here. And then the high mobility has been attributed to the stacking of the backbones in this orthorhombic structure. So we know that singlet fission has been observed in this orthorhombic crystal form of rubrene. However, it's not very efficient. So we also know that rubrene has two other forms, a monoclinic structure here and a triclinic structure. So the question is whether one of these other lesser known forms of rubrene might exhibit more efficient singlet fission. So here you can see the band structures of the 3 forms of rubrene. And you might notice that the band structure of the monoclinic form is significantly different than the other 2. So in the orthorhombic and triclinic forms, we have a smaller band gap and a larger band dispersion than the monoclinic form, which has a larger band gap and very flat bands. And we can attribute these differences to the coupling between molecules in these different crystal structures. So the frontier orbitals of rubrene are actually localized on the tetracene core. And in the monoclinic structure, there's no overlap between the tetracene backbones of different molecules. So that means the coupling between molecules in this crystal is weak. And therefore, we get these very flat bands and a larger gap. So now the coupling between molecules in the crystal is also going to affect the nature of the exciton wave function. So exciton wave functions are actually two-body wave functions. So what you're seeing here is the electron probability distributions around a hole which is marked by a red sphere here. And we can classify excitons in molecular crystals into two types. The first type is called a Frankel exciton, and this is where the electron density is concentrated around the hole position. So this one, for example, is a Frankel type exciton. The other type is called a charge transfer exciton, and this is where the electron density is concentrated away from the hole position. For example, this one here is a charge transfer exciton. So in real materials, you actually get excitons with a mixed character, and the degree of mixing depends on that coupling between molecules. So in the monoclinic form, because the coupling is very weak, you get a singlet exciton that has an almost pure charge transfer character, and this is actually considered good for singlet fission because, as you may imagine, it might be able to couple more strongly to the triplet excitons on these neighboring molecules. So finally, we're going to look at the energy criterion for these different polymorphs of rubrene and compare it to pentacene, which is the quintessential singlet fission molecular crystal. And what you can see here is that the monoclinic form is closer to meeting the energy conservation criterion, and also it's pretty close to pentacene. And this is why we think, based on our calculations, that the monoclinic form of rubrene might exhibit very efficient singlet fission, possibly rivaling the efficiency of pentacene. So, to conclude, crystal packing significantly affects the electronic and excitonic properties of molecular crystals, and then through computer simulations, we might be able to figure out how to pack molecules in an optimal way to modify the electronic properties and achieve the properties we want, for example, more efficient singlet fission. And this is my group at the Warhol Museum. We have open positions for PhD students. And you can read this haiku on van der Waals interactions if you like.